Good morning, everyone. My name is Yohana Muhammad. I'm a student of Makere University. I'm here today with you to share my project that I have done with my members, with my teammates. So it's about mobile acoustic intelligence for privacy preserving clinical audio AI for cardiac decompensation. Like you try to build an app, that is going to detect and predict heart failure. So you have our presentation roadmap, you have the introduction, you have the related work, problem statement according to our data set. You have the research question and objectives, research contribution, methodology, system architecture and mathematical foundation of each of the created models. You train 8 models, so each model you are going to give it architecture and mathematical foundations. You have the dataset description, you have the results, you have the limitation, conclusion and future works, how to improve our deployed model. Then you have the reference and also the acknowledgement. So for the background and introduction, our project aims to develop a mobile audio-based AI solution that monitors cardiac patients in real time and predict potential decompensation risk 6 to 24 hours in advance. We will introduce each keyword by contextualizing it within the scope of our project. So the first one, you have 6 keywords. So I'm going to introduce it with our project. The first one is acoustic cardiography. This technique analyzes heart sounds such as S1, S2, murmurs, and gallops. It allows continuous cardiac monitoring in hospital wards and overcomes the limitation of traditional stethoscopes. By providing real-time evaluation of cardiac function, it supports not invasive heart monitoring. The second one, you have the beamforming and sound localization. Using an array of 4 to 6 MEMS microphones. This method applies beamforming algorithms like MVGR and GEV to isolate sounds at the bed level. It uses time difference analysis to localize sound sources, enabling accurate tracking of individual patients in multi-bed environments. This supports multi-patient acoustic monitoring. The third one, you have the heart failure early warning. This system predicts cardiac decompensation within 6 to 24 hours window using a fusion of multiple biomarkers. It generates alerts that allow early medical intervention, helping reduce emergency situation. The goal is proactive clinical response before heart failure escalates. After you have the fourth, on-device noise suppression. All audio processing is done locally using HAI, combining RNN noise and spectral subtraction techniques. No area audio is expected, ensuring compliance with HIPAA and GDPR regulations. This privacy by design approach guarantees patient confidentiality through local-only processing. Then you have the 5 point, which is a federated clinical audio AI. This approach enables model updates across hospitals without sharing patients' data. It breaks down data silos safely and supports cross-institutional learning by training collaboratively while preserving privacy. And it improves model generalizability across different clinical settings. Then the last one, which is results constraint monitoring. Designed for affordability, this system targets hardware cost under $150 and runs on low power Android devices. It supports both mobile and fixed deployments, making it suitable for results limited environments. Its scalability allows integration across hospital networks, promoting accessible healthcare. After you have the related works, you have been making some research during our work, so you have been looking for some related works that is similar to our project. So you have the paper, you have the models, you have the results from the model, you have the architecture limitations, and also the contextual limitation. For here, the first one is grazing ultrasounds using diffusion models by Tristan. That is the name of the Then the university, that is the University of Technology and Field Research. You have the model. For the model, that is score based diffusion model. Then you have the results from the model. Diffusion model achieved higher PSNR. Then you have the architectural limitation, high computational cost, training challenges. So here describing so far there are 6 related works that they are described here. Let us continue. After I have the problem statement. The problem statement according to our project, our data set. Then, so here you have the domain application problem. For our case, the domain application problem, you have the cardiac decompensation in shared hospital wards. You have late detection leads to emergency intervention. You have multi-patient monitoring with limited staff. You have privacy concern in continuous audio monitoring. Then the last one is the resource constraint healthcare settings. Then you have also the computational problem. For the computational problem, you have the real-time audio processing in noisy environment. You have multi-source separation for bed level isolation, weak cardiac signal detection and nickel noise. You have also the 6 to 24 hours risk prediction from Acoustic biomarkers. Also, then the last one is the privacy. Is the privacy preserving HAI on mobile devices. So here we outlined our problem statement, the domain application problem, and also the computational problem that help us to understand our project. You have the research questions and objectives. You have our research question. The first one is, can acoustic biomarkers reliably predict cardiac decompensation 6 to 24 hours in advance? That is the first question. The second one is, how effective is beamforming for patients level? Some isolation is in shear wards. The third one is, what is the optimal balance between privacy, preservation, and clinical accuracy? Then the last research question is, can federated learning improve model generalization across hospital environments? Then for our objectives, we have 4 objectives here. The first one is develop multi-channel audio processing for bed level monitoring. The second one is extract and validate cardiac acoustics biomarkers for early warning. The third one is implement privacy preserving HAI architecture. Then the last one is evaluate clinical utility in real hospital settings. You have the research contribution and output. You created a multimodal dataset and synthetic augmentation pipeline to train and validate privacy-safe cardiac audio air under realistic noise condition. We deployed a prototype mobile system that continuously analyzes what audio and alerts clinicians to possible cardiac deterioration events. We designed robust audio separation and classification models that isolate cardiac signals from multi-speaker and equipment noise. We developed privacy-preserving acoustic models that extract heart and lung features from what audio while eliminating identifiable speech content. After here, you have the methodology and system architecture. Here describing our system, the system architecture, how it works. So you have the patient is in what? First of all, you have the acquisition of sound from the patient. Then the second step is raw audio acoustic data from. After, you have the instructions. Then you have the count 2D 64 filters. That is the step explaining how our systems works. Up to the end, which is the final output mapping. That is here you have the model architecture and mathematical foundation. It's showing us how the mathematical foundation of our system. Then here you have the spectral temporal graph neural network for cardiac audio analysis. That is one of our model you have been training. So you have the actor who is going to put the input. That is how that is describing how the thing works, the architecture of our model. Also here, that is the second model with always system. Without wasting time, let me just go through because you have a lot of slides to cover. cross-model audio graph, that is also an model. Yeah, contrastive audio graph networks, yeah, also. Yeah, then here you have the dataset descriptions and exploratory data analysis. The first one, so our data set, you're going to give some information about our data set, where we took it from. So the dataset description, the official name, that is Digiscope phonograph sorry, phonocardiogram dataset. Then the source, that is Physionet Challenge 2022. So our dataset includes recordings from 942 unique pediatric patients. In total, there are 3,163 phonocardiogram audio files, with each patient contributing between 1 and 7 recordings, averaging approximately 3.4 recordings per patient. After you have the exploratory data and analysis, so you have used Cargo notebook to do our code. So here we are going to explain how we handle our EDA. So our EDA process with setup and import statement, followed by data loading, missing values. Then our missing value analyzed to assess data quality. The univariate analysis is performed using statistical summaries and visualizations are created to explore individual features. Then you have the second one, which follows, that is combining statistical tests and visual plots to examine relationship between variables. The next, the data undergoes cleaning and feature engineering to prepare it for modeling. Custom audio processing functions are defined, and batch extraction of audio features is executed. Then the extracted features are integrated with the main dataset, followed by final pre-processing step, including scaling. Finally, the data is split into training, validation, and test split and exported for modeling to avoid those underfitting and overfitting. Then here, that is a visualization of our missing value, how you analyze it, showing us from you have the age, you have the weight, you have the height. The total missing value is 11,128. After you have the univariate analysis, which showing us the normal, which represent 51.6%, then the abnormal represent 48.4%. You have also the target, which is normal distribution, showing us the unknown, the present, absent. You have the age category distribution, you have sex distribution. For female is higher than male, as you can see. Then you have the height distribution, weight distribution. That is the here is still the univariate analysis. You have the pregnancy status, you have the top 10 recording location combination. It's describing how that our dataset is. Then here you have the second point for the bivariate analysis visualization. You have the outcome distribution by mama presence, outcome. You have also the outcome percentage by age category. You have outcome distribution by sex, height distribution by outcome, weight distribution by outcome, and also the height versus weight by outcome. Here is showing us the systolic mama timing, also the outcome distribution by campaign. Here you have the result in discussion. As I said before, we train 8 models. So here you are going to provide the output of each of our model, from where you are going to choose the best one which you are going to deploy. So the first one here, that is STGNN model. You have the training results with the validation. So the final training accuracy is 0.7143. You have the final validation accuracy also, which is 0.16. Then you have the final validation. Everyone is score, that is 0.59. So you don't have a lot of time. Let me just try to go through. I'm exceeding even the time. So here you have the so here you have the fourth model. It's also displaying for us the final training accuracy, the final validation, also the final validation accuracy. After you have that is the fifth, the sixth, you have model 6, 7, and 8. Here is our result in discussion. So among the 8 train models, you have the CM, AGT, and TA. GCN stand out with the highest score, indicating a strong discriminatory power in detecting cardiac anomalies. So you have the key takeaways. The first one, that is the CM, AGT is the top performer overall. Then the second one, that is a TA, JCN matches CM, AGT in Europe, suggesting strong classification boundaries. The third one, that is the TGCRN, may need architectural or training adjustment. Ensemble of hybrid strategies could leverage strengths across models. Then you have the table of results. It is showing us the results for each model, here. Then you have the model deployment. So for us, we decided to deploy the model selected, that is multi-channel audiograph networks. According to the accuracy we got, we decided to train it. You have our limitation. Then that is a conclusion. This study explored multi-deep learning architectures for pediatric heart murmur classification using phonocardiogram data. So the challenges included data imbalance, variable recording quality, and limited interpretability. These limitations suggest the need for better preprocessing, more robust training strategies, and explanation model design. Then the future works. Future research should explore ensemble methods to combine strengths of top performance model, applying advanced data augmentation and denoising techniques could improve robustness. So our product, our model you deployed it, is working well, but it needs some, we have to improve it for better results. Then after further acknowledgement, we would like to acknowledge the support and guidance provided by our supervising professor throughout the research. We also appreciate the contribution of fellow students and collaborators who assisted during model development and testing. Thank you so much.